My name is Radmila Sazdanović, and I guess we don't really have a course title. But if I was to give this a course title, it would be a title titled Khovanov Homology and Categorification. And I hope that you know, by the end of this week, you'll be pros in it. It's a very recent and rapidly developing area of mathematics, and I'm very grateful to the organizers for the opportunity to share these things with you. Okay, so the outline of the course, I guess the whole course, is that today I'll sort of briefly go over classical invariants. I will play a little bit with the interactions between algebra and topology, and why does it make sense to actually use algebra to study topological objects. And then you'll have a crash course in Khovanov homology, so we'll learn about Khovanov homology. And then the rest of the course, I guess tomorrow and on Wednesday, we're going to really have get our hands dirty, right? And like work really hard to understand the structure of Khovanov homology and its properties and what it actually gives to us. And then we're going to step back on Friday, or I guess step out on Friday, and sort of give a big overview because of homology theories of knots and links, so homology theories in topology, but a more recent one. I don't mean singular topology, and categorification in general. So, what is this whole categorification business? What can be categorified, and sort of what are the interactions between these various homology theories? And one thing that I really like about Khovanov homology, and I'm definitely biased, is that, well, I guess about whole knot theories, right? So if you tell somebody you're interested in knots, they don't really know whether you're doing combinatorial topology, or you're a three-manifold topologist, or a four-manifold topologist, or you know, whether you study representation theory actually. So that's reflected in the number of definitions of Khovanov homology, and you know, maybe symplectic Khovanov homology, or you know, the one by Witten that sort of builds on PDEs. If you know, I have only time to say about a few of them, but fortunately, Luke Kaufman, who is here, will also be talking about Khovanov homology, and but you know, sort of we're going to have a complementary, somewhat overlapping views, and I think extensions to virtual knots and links for sure. And well, not extensions, but sort of homology theories for virtual knots and links. And then for tutorials, you will be in very good and capable hands of Dan and Alex. And I see Dan, and I see Alex too. Okay, perfect. And the tutorials will sort of have a range of problems, from, you know, let's figure out what the background for this whole business is, to let's fill in the details and understand all of these things that she did not explain well in the lectures, to here's an actual open research problem, let's work on it. And if you're interested in Khovanov homology, but it's the first time you're hearing about it, I promise that by Wednesday you're going to have all of the tools to attack the research problem. Okay, if you have any questions, please don't hesitate to let me know and interrupt. So are there any questions? Okay. So introduction to link homology is actually going to start with a brief overview of knot theory. Usually people sort of present the Lerna seal. I'm actually starting with the snake with interlacing colli from Mesopotamia, and it's this old, and then something that you're maybe more familiar with, and this is one of Leonardo's knots, and you know, he must have worked really hard, and I think this sort of it's one of the open problems. I'm joking. It's not an open problem anymore. Is to recognize which knot or link this is, because just recently Ken Millett and and names disappeared, and Hoya sort of published this paper in which they determined the types of these knots, how many cross-6, what kind of knot they represent, and so on and so on. Of course, it's not in the tables. Okay. It's too complicated. And then these are some of the Celtic knots, and these are actually very symmetric, either drawings in the sand or pictures that you obtain by putting rice flour or sand in front of your home. And some of them are actually conversation pieces, sort of like if you're having a conversation, then, you know, instead of twiddling your thumbs or like doodling or something, you actually are supposed to draw this very, very symmetric figure. And, you know, if it doesn't end up being a closed knot, then you're not really like worth having conversation with, right? So it's very stressful. But apparently everyone in society knows how to do it. So it's definitely a diagrammatic technique that you can develop. So history of knot theory is sort of kind of modern, more modern, less modern, postmodern, pre-modern. Knot theory starts with 1833 when Gauss develops, well, the Gauss linking integral for computing linking a number of two knots. Lord Kelvin had a theory of vortex atoms. And then can everyone see this? Because I cannot, right? Yes, okay, very good. Makes sense. With Tite and Kirkman and Little, which had the first tables of knots up to 10 crossings. We can do much better now, but the number of knots sort of increases dramatically as we increase the number of crossings. I'll skip this slide. This is just one of the pictures from Rob Shorain's knot plot, just to advertise the workshop tomorrow. It's wonderful software. But you know, here's what knots and links are. They're just like S1s embedded in R3 in sort of some nice ways, and we do want to distinguish them. So 20th century knot theory brought a lot of developments. So in 1923, Alexander discovered, well, the first knot polynomial. It was kind of categorified, and don't let this confuse you, right? He actually constructed the Alexander ideal first, and then the polynomial was a principal generator of an ideal. And then in 1928, Rademeister actually gave us diagrammatic tools for studying knot theory. So you know, maybe it's good, maybe it's bad, but it's hard for most people to work with three-dimensional knots, although there exists higher dimensional knot theory too. Kurt Rademeister gave us theorems that says, well, okay, if you don't like to work with knots, then you can basically work with four-valent graphs that are somewhat enhanced, meaning when you draw two pieces of string and they intersect, you'll sort of make sure that you know which strand goes over, which strand goes under. So those basically are knot diagrams, just sort of graphs with a little bit of extra information, meaning heights. In 1938, Max Dehn developed a method called surgery of knots that Mariel mentioned as one of the tools that biologists use. Developed a method where by surgery of knots, I'm not going to say what it is, but sort of you do something to a knot, and then you basically can get all three-dimensional manifolds. And that's why people who don't care about knots per se may care about them, because the way of classifying knots can lead to classification of three manifolds and can actually be used to study four-dimensional manifolds too. And then in 62, Licorice and Wallace proved the following theorem, that every closed connected oriented three manifold can be obtained by the surgery of link in S3. So that's sort of like a completeness theorem. Okay. And then in 1969, John Conway discovered a diagrammatics for the Alexander polynomial. So as I said, the Alexander polynomial was not originally, you know, having the skein relation. John Conway came up with it, and so sometimes it's called the Alexander-Conway polynomial. And then in 1984, Von Jones did relate knot theory to physics again, and came up with the Jones polynomial that's an integral part of Khovanov homology. It's like the knot invariant that Khovanov homology builds on. So I'll definitely talk about that too. So the main question is like, when are two knots the same? And I'm sure that most of you are familiar with this, so I'll just go over it quickly. Two knots are the same, and the word for that is isotopic, if they can be smoothly deformed to each other. And then the question is, well, when are two knots equal? So you have an option of actually constructing isotopy from one knot to another. Or you can use Rademeister's theorem that says, no matter which diagram of a knot or link you take, if you take another diagram of the same knot or link, there's going to be a sequence of Rademeister moves that relates one to the other. And that sounds like a dream come true, because there's only three moves. One, when you either introduce or remove a kink, and it can be either this kink or the other one. I only drew one. So that's the first Rademeister move. The second Rademeister move says that if you have a strand completely going over the other and they have just two crossings between them, you can pull them apart. And again, I'm only showing one version of each one of the moves. And then the third randomizer move says that if you have a strand completely over or completely under the crossing, you can sort of move it to the other side. So here's the crossing, here's the strand. This strand, vertical strand, is completely on top of these two horizontal strands. So I can just slide it on top of the crossing, and now this crossing is drawn here, and the strand is to the right of the crossing. And you can do the same if the strand is on the bottom of the crossing. And again, I said it sounds like a dream come true, except that there's no algorithms for sort of determining what the sequence is. And the caveat is also that the third randomizer move does preserve the number of crossings, but these guys can change it. In particular, they can increase it. So even the bounds on how complicated you need to make one diagram in order to reduce it to the other diagram are horrible, okay? Meaning exponential. So there's still an open question of how to distinguish knots. In this sense, the question is like, well, how to determine that two knots are different? And you know, one way is to show that there is no isotopy, which is, you know, even a more hopeless problem than constructing one, right? Maybe we should come up with something better, and you know, smart people did come up with something better, and that better is called a knot invariant. So what are knot invariants? It's some property of a knot, so some value that is same for isotopic knots. So if you have two knots that are the same, then their values have to be the same. The values of the invariant have to be the same. But there's of course catch 22. If you compute the invariant and you get the same number for one diagram and for the other diagram, then you don't know if they had to be the same. So knot invariants can tell you when two knots are different, but if that particular knot invariant gives takes the same value on two different knots, on two knots, right? Then you cannot say for sure that they're the same. Okay, so you have to come up with yet another knot. And examples of knots include numerical. So I've kind of ordered them here in increasing algebraic order of complexity, okay? So nothing to do with computation. So numerical, let's say number of components, linking number of p colorings. I won't go into details. Of course, there's the unknotting number, of course, that I somehow managed to miss from here, but that's probably going to be the last open standing question on theory. And then it can be polynomials, right? So polynomials, you know, hopefully with integer coefficients, but there's Alexander-Jones, well, many versions of the Kaufman polynomial, of course, Homology PT and SLN polynomials. And then what's interesting, and you can already see this here, there's a number of p colorings, but then if you actually dig deeper, you actually see that there's not only numbers of p colorings that actually form a group. So you can have a group formed by p colorings of a knot, and then of course there's a knot group, which is fundamental group of the knot complement. And then there's the Alexander modulo, there's quandles, they're not quite groups, but I did sort of put them here because they're almost groups. And then there's homology theories, and you know, again, this is, you know, less than 2 decades old. Okay, so I could not help putting a quote from someone from Göttingen, right? So Hermann Weyl says that in these days, the angel of topology and the devil of algebra, well, abstract algebra, fight for the soul of each individual mathematical domain. I'm not sure that that's true. I'm not sure who's the devil, who's the angel, and you can, you know, pick your own devils and angels. But you know, in general, I believe that competition is good, and I'm sure that sort of biologists would agree, right? That's where the progress happens. So actually, you know, the area that I'm working in is sort of like comes from symbiosis of these two. Okay, so why algebra? Well, topological objects are great. I think most of us will agree that it's good if you can visualize something, although pictures can lie. And picture is usually not the proof, but that's debatable. But then they're hard to compare, right? And algebraic objects are easier to compare. And then sometimes, just sometimes, they're diagrammatic. So there's planar algebras, there's visualizations of algebras, and those are the ones that we'll be working with at least this week. And the idea is, of course, to map topology to algebra in such a way that we don't lose information, okay? And hopefully we retain a lot of information. So the way to say that mathematically is that you construct a functor from a category of topological spaces, and, well, continuous maps or whatever maps you want to consider into some algebraic category, let's say vector spaces and linear maps or groups and group homomorphisms. And then if that functor is faithful or somehow otherwise good, then if whatever was reflected in topology will be still captured when you start trying to compare these algebraic objects. So instead of comparing topological objects, you're going to compare these algebraic quantities. So for example, you know, you can if you want to distinguish a two-component link from a knot, well, all you need is the number of components, right? Great. So no knot will ever be equal to a three-component link. Okay, but you know, that's a very good version. So, but usually invariants sort of can be very different in nature, and sort of the best ones are the ones that actually provide connections between different properties of a knot. Let's say a combinatorial property of a knot and some, you know, maybe geometric property of a knot. Okay. So time to actually get to work. So Jones polynomial. Well, I'm kind of going to hide a little bit the details about the Kaufman bracket polynomial. But basically, what I'm giving you here is definition of the Jones polynomial that goes through Kaufman bracket polynomial. So what you see here with like square parentheses is the skein relation for the Kaufman bracket polynomial. So what does it say? If you have a link diagram that I'm denoting by L plus, and that basically means that I'm hiding everything but one crossing of a diagram. Okay, and then everything that's invisible stays intact, and I only change this crossing, and I change it, well, in one of the two ways that kind of Mariel hinted at. I destroy the crossing either by reconnecting top to bottom or left to right. So you kind of think of these endpoints as being fixed. Well, those are called smoothings, and there's two different types of smoothing. So what this is telling you is that the Kaufman bracket polynomial of the knot that has this crossing is just a linear, well, not a linear combination, but it's a combination of Kaufman brackets of two simpler ones, in which everything stays the same except that this crossing is destroyed, and it's either destroyed in this way or this way. Okay, so what's really great about this particular skein relation is that you definitely express the polynomial of a knot in terms of polynomials of two simpler knots, where sort of simpler means that it has fewer crossings. Okay, so eventually you can kind of think of, well, I can build any knot from a non-knot, just from a circle, right? Well, a combination of circles, sorry. And then what I'm saying here is that the Jones polynomial is just some sort of shift of the Kaufman bracket polynomial, and how much you need to shift depends on the right. This says that the value of the Jones polynomial, and again, it just depends whether you're thinking about the normalized or unnormalized one. I'll consider this one where the value of the unknot is q plus 1 over q. And then this says that if you want to compute the Jones polynomial of the link, this joint union, the unknot, well, you just multiply the Jones polynomial of the L with the value of the unknot. Okay, and those are all of the rules that you need to compute the Jones polynomial. Okay, but so this skein relation sort of says, what do? I give you a knot diagram, and you pick a crossing, and you destroy it. Then you get two diagrams. Then each one of these two diagrams, you pick a crossing, you destroy it, you get 4 results, and then you repeat and repeat and repeat and repeat. So, but there's another way of doing this, is just think about it. If you have n crossing knot diagram, each one of them will be resolved in 2 ways. So that means if you want to resolve all of the crossing, you have 2 to the n possibilities. And here I've drawn all of them for you. Okay? So trefoil has 3 crossings. So that means that we're going to have 2 to the 3. So 8 possible complete resolutions. So what do I have here? In which one of these crossings are resolved vertically, which means that I'm going to get 1 loop here, 1 loop here, and 1 loop here. So they're roughly going to look something like this. So they're all resolved in the same way, and I get just 3 loops here. So now what happens if, let's say, I change the smoothing of this crossing, and instead of it being this way, it's perpendicular to it, so it's this way. So what's happening is that these 2 circles will merge. I guess this is a good point just to remind, I think most of the people do know this, but sort of like if I have the trefoil, okay, and then the first resolution looks like this, and I'll call this 0, 0, 0. And then let's say I need to decide on the ordering of the crossing. So let's say that this is the first one, this is the second one, and this is the third one. Then I want to get to the state, which is 1, 1, 1, which sort of means that all of the smoothings actually look like this. Well, in that case, what I'm actually going to get is this circle and this outside circle. And that's diagrammatically shown here as just two concentric circles. And then there's like a bunch of them in between. So if I want to find a state that's 1, so let's put 0, 1, 0. Well, that means that I have to switch this smoothing into the one that's perpendicular to it. So I'm going to have two that look like this, and this one that looks like this. And then I just smooth everything. So smooth so the things sort of bounce off of this, and along and along. So these are the two circles that I've drawn up there. Okay, makes sense? And then what happens? Well, we know what's the value of the circle. So if you have 3 circles, that gives you the third power of q plus 1 over q. If you have 2 circles, that's the second power. 1 circle was just the first power. And then what kind of hiding under the rug is that sort of like going this way, so we pick up some power of q. Okay, according to the Skene relation, and you just sum all of these up and you get your Jones polynomial. Okay, that's so-called state sum formula. Oh, sorry, this should have been just times 3. Sorry, times 2. I'm already categorifying, sorry about that. Okay, it just sneaked in there. You'll see a picture like this in like 3 slides again. Sorry, this should have been just squared, but thank you for pointing that out. Okay. So what's the motivation? So I have like a bunch of circles, and I want to upgrade the Jones polynomial into homology theory. And you know, if you did have some algebraic topology, homology theory means that you somehow are going to assign groups or at least vector spaces to your topological space. So I somehow need to find some spaces here. And here's the way. So let's think of category of cobordisms, n-dimensional ones, not that we will need n-dimensional ones. And again, this is going to be one topic that's going to be covered in the tutorial, so I'll just go briefly over it. So objects are closed-oriented n-1 manifolds. Morphisms are oriented n manifolds with boundaries. Okay, so let's think. What are going to be cobordisms in degree 1? Objects are going to be 0-dimensional, so they're going to be points. And the actual morphisms will be oriented 1 manifolds with boundaries. Well, those are just line segments, right? That's the only thing you can have in 1 dimension that has boundaries. Okay, so an n-dimensional TQFT is an it's a kind of an algebraic upgrade of cobordisms. It's a tensor functor from coband to some additive symmetric monoidal category. Okay, don't worry if you're not familiar with these words, don't worry about it. But here's how it works, an example that I've sort of just said. So a functor is denoted by f, and what I'm going to do, I'm just going to assign a vector space to a point. Okay, and then I'm going to say, well, if I have a cobordism between these 2 points that looks like this, and let's sort of assume that it's going from bottom to top, well, I have nothing here. That will give me just the base field here, and I have 2 points here. Well, each point has a vector space assigned to it, so I'm going to have a tensor product, direct product of these 2 vector spaces. If I flip the picture over, then actually, again, things go from bottom to top, so I'm going to get a map from 2 copies of a vector space up to a field. And let's say if things go from bottom to top, okay, what kind of map am I going to get here for this one? Oops. Okay. Okay, this one, right? No? No, please stop. Please. Okay, what kind of map do I get? Okay, someone has to say something. It's the identity map, so from V to V. Just the identity map, nothing happens. Okay, and then if I have something that looks like this, we're topologies, right? We can just train it. It's the identity map. Okay, fine. Okay, so what's beautiful is that there's a theorem that says unoriented one-dimensional TQ of T's over some field K correspond to finite measure K vector spaces with something that's called a non-degenerate bilinear form. It comes from straightening out homotopies, okay? So we need to up our game a little bit because what we have there given to us is just a bunch of circles, okay? Sorry? Yeah, so this is basically what tangles sort of are built of, except that you need to put orientations if you want oriented tangles in this way. Okay. So here's this sort of algebraic view of the algebraic structure that we're going to be using. So it's called the Frobenius algebra. And again, I really will not go through these definitions, but you know, it says it's a finite dimensional unital associative algebra equipped with a non-degenerate bilinear form such that, well, it's associative. Okay, great. Or you can think of the algebra with multiplication, co-multiplication unit, and co-units such that certain conditions are satisfied. And then you look at the definitions and you say, are these like really equivalent? Okay, well, you know, it's something to prove. But examples include some, you know, familiar algebras like matrix algebra with a trace, like we all worked with it and see them in linear algebra. But here's the way that I like to think about it. So Frobenius algebra for me look like this. Okay? Well, what do I mean by look like this? They're generated by two-dimensional cobordisms. So again, this piece is something that sends a circle to nothing. So it's an equivalent of sending a point. Well, you cannot send a point to nothing, but I guess I have 2 points to nothing. So this sending a circle to sort of nothing gives you a map from your space, let's say vector space, to the base field, okay? Or from a group to sort of a base field. Cup is the opposite one, and then this map says you have 2 inputs and you have 1 output, so that's going to be multiplication. Let's say I label this with 2 and this with 3, and then the output will be 6. Okay, well, not that simple, but something like that. And this is the co-multiplication. So nature wants to have natural ways of splitting one thing into 2. So I want to be able to split one circle into 2 circles. And then this is how I see, for example, the associativity. You have 3 inputs. You leave the first one alone. You merge the 2. And then you multiply the result of this merge with the other one. So this is what A parenthesis B times C is equal to A times B close parenthesis times C. So this is a pictorial way to see associativity. And there are all these other beautiful sort of relations that sort of hint at least that there's a projection between things that are called two-dimensional topological quantum theories over some field K and commutative Frobenius algebras over the same field K. So why am I telling this to you? Well, because Khovanov homology, kind of for trivial links, can just be built off of this duality. So what you say, Khovanov homology of an unknot will be your base field or your commutative ring R, so maybe Z. And then the value of the unknot, well, will just be, and this should have been KH, will just be this A, commutative Frobenius algebra over the base ring. And then if you have a trivial K component unlink, you're going to take K tensor copies of your algebra A. Okay, that's for the trivial links, and it's not yet related to the Jones polynomial. So how am I going to relate it to the Jones polynomial? Well, here's the thing. The Jones polynomial of the unknot is Q plus 1 over Q. Okay, well, that's the graded dimension of your algebra A if your algebra is graded, and our algebra will be graded. Well, what that means is that, for example, for Khovanov homology, the unknot can be equal to Z of X quotient by X squared. And I do claim, it's something that you need to prove, that it is a commutative graded Frobenius algebra where degree of X will be -1 and degree of 1 will be 1. So it's clearly generated by 1 and x. And then let's say what happens. If you multiply 1 and 1, you get 1. If you multiply 1 or x times 1, you get x. And then if you multiply x and x, you get x squared, but x squared is 0. So that dies. And then co-multiplication sort of says, well, if I have one circle labeled 1 and I split it into 2, then, you know, the Frobenius algebra structure tells us that we're going to have a combination. One circle labeled 1, the other circle labeled x, or the other way around, this labeled x and this labeled 1. And x splits into x tensor x. And then there's like a beautiful fact that the degree of this algebra map, either multiplication or co-multiplication, is equal to the negative Euler characteristic of the corresponding cobordism. And you know what I did not say is that this inverted pair of pants, and you know in topology, this guy is called pair of pants, and this is copants or inverted pair of pants. Okay, so so topology is well dressed. But here's the way to sort of dress up the computation of the Jones polynomial. Okay. So what are we going to do? Well, each circle was contributed q plus 1 over q. Okay. Now we're going to replace that with a copy of our algebra A, z of x quotient by x squared. So well, let's strip down first. We have this hypercube that's 2 to the n. And then we have all these circles in here, but now we're going to label them by elements of the algebra. Okay, great. But now what's better about this picture is that there's no maps between numbers. You can add numbers, you can divide numbers, multiply, subtract, and so on and so on, but you don't have maps between numbers, but you have maps between vector spaces and algebras. And we will indeed have the maps. And somehow my slides are not showing here. So basically what I'm saying here is that up to here, up to this level, what's happening is that the number of circles is decreasing. So here, going from here to here, I merge these two circles. That means that if this was labeled 1 and this was labeled x, then this circle here would have a label x, for example. Okay? And that works here, that works going from here to here, because we go from 2 circles to 1, or from these 2 circles to 1, but not here. Here's where we're splitting one circle into 2, and that's where the co-multiplication comes into the play. So we really do need that other map. Okay? And then, of course, what you're going to learn in the tutorial is that not only do you have, in your Frobenius algebra, you don't have only an algebraic structure that comes from multiplication in a unit, and the co-algebra structure that comes from co-multiplication in a co-unit, but they sort of have to play nice with each other. Okay. By the way, like the co-algebra, or like the sort of splitting one thing into two, sort of that sort of most famous example comes from, like, you know, playing with cards, like when you shuffle cards and you distribute them. So actually there's something called the shuffle product and co-product and so on and so on. Okay, but what's the Khovanov chain complex? Well, pictures like this, where the circles are actually labeled with elements of algebras and all of their combinations, are called enhanced Kaufman states associated to this one. There's 2 to the n of them. And then the Khovanov chain group is just direct sum, and you know, you don't still know what Ci and J is, out of all of these free groups freely generated by Kaufman states. So there's going to be a picture here, but basically what we're going to do, we're going to sum along columns. Okay, and then to get the differential, we're also going to sum all of these maps. So each arrow will be a part of the differential that sends this group to this group that's sum of 3 different ones. So how are we going to define that one? Well, again, the Frobenius algebra structure tells us how. If you have 2 circles labeled 1 and they merge, well, the resulting circle will be labeled 1. If you have so you think of just the top one. If this circle was labeled x and this circle was labeled 1, then the resulting one will be labeled x. And if you merge 2 circles that were labeled x, well, that just dies. Gives you nothing. Okay, does it make sense? Somewhat? Any questions? Okay. So here's the sort of like overview slide. I'm ignoring the gradings, I'm ignoring this sign here. But basically the bottom line is that there's two n resolutions, so they fit in the n-dimensional cube. Each one of the cube is assigned, so the edges carry either multiplication or co-multiplication on them. And it turns out that each square is actually commutative, but you actually want it to anti-commute. And the reason why you want it anti-commute is because you want the differential, and this is homology theory, so d squared needs to be equal to 0. You want d squared to be equal to 0, so you sprinkle signs to make each square anti-commute, and that can be done in a very easy way in this version of Khovanov homology. And then it turns out that there's anti-homology. It doesn't depend on any choices we made. Orderings of crossings, how we sprinkle signs, nothing. Okay, so this is basically the homology theory. And there's another version of it. Well, another definition. There's many other versions of it, but we'll talk about them tomorrow. So there's a, I think, very insightful approach to Khovanov homology that I think did sort of spark a lot of interest in this theory. It's a paper from 2002. Dror Bar-Natan wrote it up after meeting with David Kazhdan and Dylan Thurston, where he said that they planned to understand and extend Khovanov homology within a week. And then he says that they barely managed to understand it within a week, but they sort of think that there's something really good about it. So here's the way to, a slightly different way to build it. Not from, it kind of again gives you a hypercube, but sort of gives it in a different way. So what's the approach? So you can think of certain normalization of the Jones polynomial, and that one says that the Jones polynomial of the empty Noether link, and we sometimes need this object, is equal to 1. And then you can just assign to it, well, kind of just your ring or the field, but slightly upgraded, and this is going to be explained in the 4th lecture, where you assign to it a very, very, very short, the shortest possible chain complex, which has just 0 goes to z goes to 0. Okay, and then Jones polynomial of the unknot is q plus q to the minus 1. Okay, well, what you say here is, okay, q plus q to the minus 1 is the graded measure of algebra A. This corresponds to 1, this corresponds to x. So I can assign 0 goes to A goes to 0 to my unknot. And then the way that I want to lift this operation that says that this joint union of links on the level of the Jones polynomial corresponds to the multiplication, the value of the unknot times the value of the link of the Jones polynomial. Well, that's going to be upgraded. The multiplication is upgraded to the tensor product. Okay, so again, this is the value of the unknot. This is the Khovanov homology of a link. And then finally, you need to lift the Skene relation. And again, here I gave you a different version of Skene relation just because I'm following Bar-Natan's construction, which says that now the Khovanov homology of the link with the positive crossing is equal to the total homology, well, and that's has been seen in taking the homology of the whole cube, of something that's called a mapping cone construction. So I have the Khovanov, sorry, this should have been a chain complex. Chain complex associated to L0, to one smoothing, that's mapped to the chain complex of the other smoothing. And then there's this map that comes just from the saddle cobordism, one that sends one smoothing to the other smoothing. So, oh my God, I won't be able to draw a saddle, but let's say you send this one to this one. Okay, and you can imagine a saddle cobordism between them. So just induced by this one. There's some certain shifts that I'm sort of shoving under the rug. But basically what this means is that each one of these would kind of give you the edge of the cube. So either multiplication or co-multiplication, but sort of this is a topological way to view it. However, if you look at so this is given in a Jones Dror's paper on Khovanov's categorification of the Jones polynomial. Dror has another paper in which he gives something that's called the geometric complex construction, in which he literally works with cobordisms and sort of a geometric picture that corresponds to this and gives purely geometric relations to this. I'm sure that Lou is actually going to talk more about this, so I'll just take it from here. And then a good thing about it is that it turns out the Khovanov homology does not depend on the choice of diagrams, meaning it is a link invariant. So how do we check that? Okay. Well, we check it since it's defined diagrammatically. We're going to check it by proving that Rademeister moves don't change Khovanov homology. Okay. Well, that's how you prove that the Jones polynomial is invariant. You take the more complicated side of the Rademeister move and you simplify it, and you see that the Jones polynomial stays the same. So we're going to do the same now for Khovanov homology, except that sort of simplification now happens on the level of chain complexes, so it's going to be slightly more complicated. So the way to view it is to actually look at the more general statement from algebraic topology. And this one says the following. If you have a chain complex and something that's called a subchain complex that is denoted by C prime, then there's a way to kind of reduce it. It's kind of like if you have a 0 in your not polynomial that's written by x squared minus x squared, well, you can just get rid of that part. Okay? Well, the equivalent of x squared minus x squared on the level of chain complex is something that's called an acyclic chain complex, the complex that has no homology to it. Okay? So the first lines here says that if you have an acyclic subcomplex, then the homology of your original complex is the same as homology of the quotient, where you sort of just remove that acyclic part from your chain complex. Okay, that's great. But sometimes maybe this subcomplex is non-trivial, has non-trivial homology, but then if the quotient is simple, if the quotient has no homology, then you say, well, great, because everything that was important about my chain complex is actually contained in this smaller subchain. So then it means that homology of the complex C is the same as homology of the C prime. Okay, so I encourage you to look at Dror's paper and the proofs of invariance. I'm actually going to go through the invariance of the Rademeister move 2 for you. Okay, so if you follow this sort of line of reasoning, then what you're going to get, so I want to show that Khovanov homology of this guy. So again, I'm hiding everything in the link except for this particular part is isomorphic to the Khovanov homology of this guy. Okay, well, I'm going to see what happens, what gets assigned to the Khovanov homology of this guy. I have to destroy these two crossings. But now for the first time, and I kind of shoved it under the rug, these two crossings won't have the same sign. One of them will be positive, one will be negative. So sort of resolving them, you have like, well, 4 different options. So let's see what are our options. I can sort of do one of them this way and the other one this way. That's sort of the same sort of thing. Or you, oops, I did not want to do that there. Okay, let's do it here. And let's do it the other way here. And then you can have mixed ones. Okay, and see what the resulting values are. Or when we do the smoothings, the pieces of a circle you're going to get are sort of this one, and then this one. Okay, and these are the main players in the total chain complex that's shown up here. So this is our starting chain complex that corresponds to the Khovanov homology of this one, and I'm hiding everything else, okay? And I want to somehow simplify it, okay? So I basically want to use this theorem, okay? So again, you won't be able to sort of see that right away, but you can think of this particular chain complex. So what is this chain complex? Well, if you look at this piece here, it has this special circle in the middle. Okay, so that special circle can be labeled with either 1 or x, or in Dror's notation, which I'm following here, is v plus or v minus. Okay? So if you label it by v minus, then the sort of this multiplication here is actually isomorphism. Okay? That's the one that sort of sends x to x tensor x. And if you look at this, because this is an isomorphism, that this whole thing is acyclic, has no homology. So if I want to compute homology of this guy, I can just quotient out this piece. What do I get when I quotient out this piece? Well, this piece is the same as this piece, so it just disappears. I have 0 here. When I subtract the circle labeled by V minus here, what I get is the circle, V plus, is the circle labeled by V minus here. And then these two bottom terms are not touched. Okay? So now Khovanov homology of this picture is the same as homology of this guy. Well, it looks simpler, but I don't yet know exactly what it is. So notice that this picture actually has a kind of trivial subcomplex where you get only this guy. This guy is actually not in the image of anything, and it goes to 0 when you think of Khovanov maps. So it just kind of stands on its own there. Okay? But this is not acyclic. It definitely has homology here. So we actually need to use this piece if we're lucky. So what I do is I sort of say, well, okay, if I quotient out this piece out of this guy, which is shown here, what I get is something acyclic. Can everyone see the bottom of the picture? Yeah, so again, this co-multiplication map is just an isomorphism here, so this is acyclic. There's 0 and 0 here. So what that means is that the homology of this guy is the same as homology of this guy is the same as homology of this guy. Okay, but homology of this guy is what we wanted to prove. Oh no, okay. This is, no. Okay, I see. Okay, if I touch the other one, is there another board behind? Okay, probably. Okay, so does it make sense? Okay, perfect. These are the types of proofs that you need to do. And then here's the punchline. Sort of Khovanov homology does categorify the Jones polynomial. So what does that mean? It lifts the Jones polynomial. Well, what does that mean? Well, that means that you can recover the Jones polynomial from Khovanov homology. How? You compute the Euler characteristic. The same you would do if you had your singular and simplicial homology or something. You know, you name it. If you compute, let's say, simplicial homology of your simplicial complex, when you compute the Euler characteristic, you're going to get the Euler number. So number of faces minus number of edges plus the number of vertices type thing. So computing the Euler characteristic amounts to taking the alternating sums of ranks. And here's how it looks like on the example of the trefoil. Okay. So if you believe me, this is Khovanov homology of a trefoil. Okay? Well, what does that mean? That means that each number 1 here corresponds to a copy of a base field. Okay? In this case, let's say Q. And so what does that mean? Well, it has 2 degrees. One is homological degree, one is the degree that comes from the algebra. And you can actually encode it as a 2-variable polynomial. So you think of this as a grid, and you say, well, in degree 1, sort of there's only q, and then there's q cubed, and then there's t squared q to the 5th, and then there's t cubed q to the 9th. Okay? The way that you get the Jones polynomial is that you substitute t with -1. That's going to give you the alternating sum of things. So basically, this is not an interesting example, but the coefficients of the Jones polynomial are obtained by taking the alternating sums of the rows here. Okay? So, you know, why work with Khovanov homology when we have the Jones polynomial? It's a pretty good invariant. Well, when you say that Khovanov homology categorifies the Jones polynomial, what it means is that it sort of can do everything that the Jones polynomial can, and you can hope that it can do better. Okay? So, for example, there's a theorem that the span of the Jones polynomial gives the crossing number of alternating knots. Well, you say, okay, the span of Khovanov homology gives the crossing number of the alternating knots. So what do I mean by span? I mean the difference between the highest homological degree involved and the highest degree involved and the lowest degree involved. That's the same as the span of the Jones polynomial. And actually, that's the same is true for adequate knots. But then you can sort of say and again, this is more or less obvious depending on which construction you use. Jones polynomial satisfies the skein relation, and that's like one of the computational tools for the Jones polynomial. Where there's an equivalent tool, just upgraded to homology theories for computing Khovanov homology. And it takes the form of the long exact sequence in homology that says that Khovanov homology of this link, and there's equivalent one for the negative crossing, that the ith Khovanov homology, and I'm completely kind of messing up the grades here, but the Khovanov homology of the link that has a positive crossing can fit, or fits in the long exact sequence of the Khovanov homology of a link with one smoothing, and then in the Khovanov homology of a link with the other smoothing. Okay, but this sort of goes, well, not infinitely because Khovanov homology is bounded, but there's a long exact sequence. And then in general, if that long exact sequence splits, let's say has a 0 here and has a 0 here, and it's split, then you can say that Khovanov homology is equal to the sum of two. But normally it's more complicated. And this and these maps are actually hard to determine. But in order to prove this, and I hope that, you know, if you're not familiar with it, you can actually do it. You can actually prove that the long exact sequence, as usual, comes from some short exact sequence. And here we sort of say just that the Khovanov chain complexes sort of fit in the short exact sequence. So you only need to prove this, and that will automatically give you the long exact sequence. But anyways, long exact sequence is one of the main tools for computing Khovanov homology. So if you're interested in that, it sort of tells you that you can compute Khovanov homology or more complicated knots by looking at the simpler ones. Okay, but is Khovanov homology actually stronger invariant than the Jones polynomial? Are there two knots that Khovanov homology can distinguish that are indistinguishable by the Jones polynomial? I mean, that's the question, right? If you're interested in classifying knots. And the answer is yes. So, for example, just look at these two diagrams, and then I'll come back to this one. So this is Khovanov homology for the 5-1 knot, and this is Khovanov homology for knot 10, 132nd knot with 10 crossings. So now I sort of, instead of writing ones, I wrote z's here, but usually this would be just a number of ones. But then there's like a z2 here. Usually in computation, just denoted by 1 sub 2. Okay? And then you want to compare these two, so their Jones polynomials are the same, but their Khovanov homologies are not. And let me point out that they're different in, well, kind of two ways. Okay? So number one, in degree -3, okay, which gives you this q to the -3, there's one copy of z that tells you that there's a coefficient 1 in front of q to the -3. But look, Khovanov homology of 1032 has a z, but it also has a z2. Okay, so actually torsion information is something that the decategorification doesn't see, right? So Jones polynomial doesn't see torsion in Khovanov homology. Just computing is the alternating sum of ranks of groups. Okay, however, even if this z2 was not here, and I want to point out that torsion is not always needed to distinguish two knots. Khovanov homology of this knot 1032 actually has two copies of z in degree -1. That's one above this one, where there's nothing here for 5-1. So there's something not trivial in the level of Khovanov homology, but you'll see this z comes with one sign and this z comes with another sign. So it's going to be 1 - 1. So it's going to give you a coefficient 0 in the Jones polynomial. Okay, so these are sort of some practical ways in which you can notice that Khovanov homology does distinguish knots that the Jones polynomial cannot. One is to have torsion, and one is to have non-trivial homology, but such that the ranks of groups are the same and they come in neighboring states, or maybe sort of they come 3 apart. So in decategorification, they sort of cancel out. Okay, however, and we're going to talk about this more, for alternating knots and links, Khovanov homology is actually determined by the Jones polynomial, and something that I think you all know about, but we'll mention, which is the signature of a link. So the actual place when Khovanov homology is really stronger than the Jones polynomial is when you look at non-alternating knots and links. Okay? But sort of from structural point of view, Khovanov homology is a functor. Okay, so what does that mean? Well, here's a pictorial way of thinking about it. So what are the objects that we're looking at? Knots and links. Okay, but knots and links are topological objects, so they come with maps between them. In this case, it turns out that you want to take any continuous map between one knot and another knot, but we're going to think of these link cobordisms that I briefly described. They sort of look in, again, okay, sorry guys, that given live in R3 cross an interval. And then the Jones polynomial assigns a polynomial to a knot or a link. Khovanov homology assigns this collection of Khovanov groups, and there's like a sort of a whole plane worth of them, right? It's bounded. But what's really good about it is that it actually assigns a map to the cobordism. It assigns a map between two Khovanov homology groups. So if you have like a picture like this, which sort of says you have one knot and you have another knot, and you have a certain surface whose boundary components are these two knots, and that surface may have a genus, well, that cobordism between them is actually going to induce a group homomorphism between Khovanov chain groups. Okay? Okay, well, how can we use that? Okay, I guess this is sort of what I've described, and actually you know what the degree of this map would be. And let's just for a second work over Q because it's simpler. So I want to prove for you the Khovanov homology of a mirror that I'll denote by L prime. Sometimes it's like L perp of a link. L is isomorphic to Khovanov homology of the original link. So that's if you work over Q. Otherwise, you have to use universal coefficient theorem. So there's many different ways to prove this, and I hopefully you will do in the tutorial. But here's a sort of cobordism view of it. So take a cobordism that sends L, disjoint union L prime into nothing. Okay, so what do I mean by that? So if this is my L, and this is the L prime, okay, this joint union means that I just draw them like this, and then I send it to nothing. So if they were just knots, I can sort of draw it like this, but I mean, there's going to be something complicated, right? These are not just the unknots, okay? I just sort of want to say that I send it to nothing, because what that means is that I can, because there's an induced map, that means that this cobordism S will sort of have a map between Khovanov homology of L, tensor Khovanov homology of L prime into, well, now it's kind of not quite a nothing, it's the empty link here. And this is where it comes in handy that what we've assigned to an empty link was the field. Okay? Q. Okay, but anyways, this is the Khovanov homology of the empty link. And I'll call this S star. And then, we're a topology, so we can wiggle this a little bit. And I guess I'm over time, so let me sort of just straighten this out. So how does it work? I'll start with L, and then I'll sort of do nothing to it and kind of bring that same L a little bit lower. Okay, and then I'll wiggle it this way. At this point, I've changed the orientation, so this is where I get L prime. Okay, and then I do another bend like this. What do I have here? It's L, and then I take the cylinder one. Well, that's L again. Okay, but this can be straightened out. And this, as Alison helped before, is the identity map. So actually, this thing that gave me a pairing between this Khovanov homology had to be non-degenerate. Okay, and then there's the algebra fact that if the pairing was non-degenerate, then actually you can work things out here, and the groups had to be isomorphic. In general, you can have this as if the tensor product of two vector spaces sort of is non-degenerate, then the vector spaces had to be isomorphic. Okay. To just wrap up, so applications of Khovanov homology, we'll talk about some of them. Khovanov homology is fully combinatorial. It has roots in representation theory, but it's very powerful in distinguishing knots and links. It sort of does capture a lot of geometric and topological informations. It's stronger than the Jones polynomial. It actually can detect the unknot. Okay, and this was proven in two different ways. We'll talk about it, and the question whether Jones polynomial can distinguish the unknot is still an open question. And for example, Khovanov homology actually provides a lower bound for the slice genus. We'll talk about that. Here are the references for this talk. Anyways, introductions to Khovanov homology have been done. There's like many of them. All of these papers are excellent introductions, and actually Paul Turner has there's one here that's missing. Paul Turner has a Hitchhiker's Guide to Khovanov homology, which is lecture notes from 2014, so fairly recent. But there's actually 4 recorded lectures online, and it's very conceptual, really, really good. And this is my final challenge for you guys. I found these guys in Freiburg yesterday. So let's be mathematical tourists and take photos of knots or links that you see around Freiburg. And let me know if you have any questions.